Hey, what's up, you guys? Come gather around, people, wherever you roam, and admit that the waters around you have grown, except that soon you'll be drenched to the bone. If your time to you is worth saving, you'd better start swimming or you'll sink like a stone, for the times they are changing. All right, thought I'd get a little song going there, you guys, because these videos can get pretty dry, especially when we're talking about kinetics and it's a lot of math and stuff like that. So what I did is this: I'm dividing actually this presentation that we would do in a typical class period into two shorter videos. That way, hopefully I can explain a little more and not feel rushed, because honestly, to do these recordings, I only have a 15-minute limit. All right, so let's go ahead and get started. So just so you know, you guys, we're going to get a little calculus on today. If you haven't taken calculus yet, that's okay. Some of you that are taking calculus right now might know what I'm talking about more than I even know what I'm talking about, because to be honest, I don't know much calculus. I took it in college and I have forgotten much of it. So yeah, so don't worry about it. If you know, you don't have to know calculus. You just need to understand that that's the tool we're using. Okay, and what we're going to do is this: is we're going to use calculus techniques to manipulate the rate law equations. So we have these rate laws, right? And where it's, you know, K times the concentrations of stuff. So we're going to manipulate those so we can do some stuff. And the reason why is this, you guys: this helps us analyze the data much better. Okay, it allows us to determine the order of reaction, and then once we know the order of reaction, we can use these integrated rate laws to find concentrations at different times and things like that. Okay, so they're much more flexible than just having the rate law. Okay, all right, so let's talk about this. We're going to deal with first order reactions in this video. So here it is. If it's a first order reaction, and we're going to keep it simple. Okay, we've got one reactant that we are looking at. Okay, we also know this, right? If we want to find rate, it's the change in concentration over the change in time. Okay, so that means this, right, you guys, that the K times the concentration of A is equal to this change in A over the change in T. So we've got that idea, right? Now, if we use what's called integration in calculus, we integrate this equation and we get this funky thing right here. And then really smart people said, hey, let's rearrange that. And oh my goodness, it's a linear equation. Take you back to algebra 1, good old y equals mx plus b. So what does all this mean, Flugum? Okay, well, that means this, you guys. We've got this thing here, right? Okay, first order integrated law, where we've got the law, natural log of the concentration A at time t, right, times the rate constant, which is now our slope, okay, times the time, plus the natural log of A at time 0 at the beginning of the experiment. So if we plug stuff into this and we get and it's a first order reaction, we get a straight line, okay? If we graph the natural log of A over T and versus T, and we don't get a straight line, it's not a first order reaction. Okay, this is a way for us to determine if it's a first order reaction by graphing or looking at the relationship between the natural log of A and the time in the experiment. Okay, so straight line versus not straight line, and we'll talk more about that a little later. Okay, so integrated graph of a first order reaction. So if it's a first order reaction, you guys, right, you should get a straight line that has a negative slope like this. And that's when we graph the natural log of A versus time. If it's first order, it's a straight line with a negative slope. Okay? Now what that means is this, right? Since K is the slope, right? Negative K is the slope. The rate constant can be found by finding the slope of the line. Kind of nice, isn't it? So let's kind of look at a couple problems that deal with this, guys, and some applications of this. All right. So first thing is this. We've got this data here. We have time and we have concentration that's decreasing of A. Here's our reaction up here. And if we look at our graph, we see that the natural log of A versus time gives us a straight line with a negative slope. Guess what? That is a first order reaction. So that means this, then our rate must be this right here. Here's our rate law. Real easy. Now, how do we find our rate constant? Well, there's a couple different ways you can do that. One way is you could find the slope of the line by looking at the time versus the natural log of A. Okay, so that's one way. Another way would be to use our integrated rate law. So I have it kind of typed up for you there on the screen. And then if I do this and I show my work here on this whiteboard, scoot back a little bit. This is just the algebra that I did in order to find the slope. Okay, that's how I got that 0.0033. And I showed the units for you there on the screen. Remember that, hold on a sec here. Remember that our units for a first order rate law are going to be seconds to the -1, or 0.0033 seconds on the bottom, right? That way we get our rate to be molarity per second. Okay, so that gives us our rate constant. All right. And then C, it says find the concentration of A at time 5.0 times 10 to the second seconds. So we can do that by, okay, if things seemed a little glitchy there, I had to go in and kind of change some stuff. I made some mistakes. So basically, here's the deal, you guys. I set things up on put things in my integrated rate law, right? And I did some math. And I found this, that the natural log of A is equal to -5.56. Oops. And still kind of have a mistake there. But then I found this, to reverse the log, right? I put this in here, -5.56 to the e to the power of that. And I get 0.0038, and that would be molarity. That would be my concentration of A at time 500, okay, at the time of 5.0 times 10 to the second seconds. Okay, so those are both ways that we can use the integrated rate law to find stuff. Got one more slide here for you guys dealing with first order reactions. Move myself down here. It says we do an experiment, right? And we look at the data, and here's our reaction right here, right? Whoops. Here's our reaction right here. And if we graph our natural log of the reactant, right, versus time, we get a negative slope straight line, of course. Well, they want to know this. What if we did the reaction at a lower temperature, right? Well, what would you expect at a lower temperature? I would guess you would expect that the reaction would happen at a slower rate, right? So that would mean this. That would mean our slope would be slightly less, a less steep line, right? Because our concentration is going to decrease at a lower rate, okay? And the natural log of that is going to also decrease at a lower rate, making our slope less steep. All right, you guys, so that's all I got on first order reactions. We're going to come back here with a second video and look at second order reactions. So